Yeah.
Oh, okay. There is some background noise, so please I would request if somebody's mics are open, please close it. If it's mine, apologies. Okay, let me share my screen. Hope this works. So I'll be sharing it full screen, so I may or may not be able to see you guys. So if you have anything you want to stop me for, or if there's any issues that come up, please let me know. Can you guys see my slide deck?
Yeah, it's visible.
Yes. Yeah.
Okay, great. So, okay, let's get started. I'll try to be quick. I had more materials than I could have presented, plus we've lost 20 minutes, so I'll be a bit quick. Uh, so, hello everyone. As Achintya introduced, my name is Shreyansh Daftry. I'm a MIT Manipal alumni from the batch of 2013. I did my bachelor's in electronics and communication engineering, and now I'm a research scientist at NASA's Jet Propulsion Laboratory. It's my honor to be here talking to you guys, and I hope to share with you today's topic on role of AI in space exploration, and in general, the excitement I have about AI robotics and the new frontiers it's opening up in space exploration. So I was hoping to give a brief overview of my journey in a single slide deck. Achintya, I think, already gave that. So born and brought up in Kolkata, I studied at Manipal, did undergrad there. Then I went to Austria, that's TU Graz. That's where I did my 8th semester internship. That was one of the best experiences I've had working with some of the best researchers in the world in computer vision. And that was my really very deep introduction to hardcore research, and I really loved it. So I continued there for another year before I started my master's at CMU in the Robotics Institute. And I was very fortunate to get my first job after that at NASA's Jet Propulsion Laboratory, right? So that's been my journey. I'm not going to go detail with on this. I think this will be more easily discussed on as a function of like during the Q&A round. I'm sure you guys have questions about the journey and how you can shape up your journey or learn lessons learned from that. So please feel free to ask me any questions about that. The only thing I'll give is a brief overview of the portfolio of the projects, kind of things I did during my undergraduate. These are stuff I started off during Manipal, but then a lot of this was internship experiences that I had. So I'll just play a couple of videos here. So this is some of the combination of work I did in TU Graz while I was there. I was working on with the aerial robotics group on computer vision. So we were building computer vision technologies and research that could allow large-scale mapping using drones autonomously. So this was just to as a reminder, this was sometime around 2013. So you can get, so drones were still coming around, autonomous drones were still not there yet, and we were building some of the first technologies for that. What you see on the center and the right is part of an internship I did at CMU while I was at Manipal. So this was this was in my third year, 2012. So that's where I got the opportunity to be a summer scholar at the Robotics Institute. And I worked on, that was my first experience working on a NASA project. I was very fortunate to work with Astrobotic at that time, which was just a 15 people team. Today, Astrobotic has turned into a 100, 200 people team with being one of the leaders in private space industry, taking us back to the moon. So it's really excitement to see where that has come from. At that time, I worked on a very interesting research project, which was for developing a team of robots that could explore underground caves on Moon and Mars. And 8 years later, 9 years later, today that project has almost turning into an actual mission. It's really inspiring some of the upcoming lunar rovers that will be happening in the next year or two. So really excited to see that all taking shape. So that takes me through the journey, which I haven't really talked much about, my experience Manipal, but to the main topic of the day, which is AI for space exploration, which is what I've been doing for the last 5 years. And I'm really excited and this passionate about this because it combines two fields that I love. So it's really artificial intelligence, and growing up, I was a space nut, like they like to call here. So I was always interested in space, anything related to space. But my technical skills growing up during my undergrad, high school, and then beyond was more in AI and robotics. That's where my interests were. So When I did graduate, this was really a dream come true to have the opportunity to combine these two things together. It's a great opportunity as well as challenging because there's a handful number of people who are working this, and I would say one of the only places in the world at that time that was doing JPL was one of the only places in the world that was doing this. So again, this was very fortunate for me to get the opportunity to actually not just work on that, to take a lead and make some have an opportunity to make some good impact in that field. So yeah, hopefully I'll share some of the work I've been doing there. So let's take a step back and see how does AI play into space exploration. So NASA, as most of us know, has a long history of building really capable machines. For the last 60 years, we as an agency have built spacecraft that have visited almost all the major objects in our solar system, from the moon and Mars to the outer planets like Jupiter and Saturn. To the extent that two of our spacecraft, you might know, Voyager 1 and 2, as shown in the picture here, are the first man-made objects to have reached interstellar space. Now, growing up, this really inspired me, and that's something I really wanted to do, become a robotics engineer that can build intelligent machines for space. But as I started to become more of a robotics researcher, gain a deep understanding on intelligent autonomy, I understood that while NASA has been building really capable machines that have done more than what most of the machines we have built in the century have done, they're not really what as a trained roboticist would yet call intelligent. Here you see two of my favorite pictures. One on the left is a picture from the Apollo missions, which carried the first humans to the moon. Now, one of the most critical aspects of the mission was landing, and that was made possible due to the intelligence of the human astronaut themselves, who manually piloted their aircraft for a safe touchdown. An extremely complex set of maneuvers that is till date very difficult for machines to accomplish on their own. Similarly, on the right, you have a picture of the Curiosity rover on Mars. While the rover is one of the most capable machines that were ever built, it is still remotely operated by a large group of humans from the mission control room here at Jet Propulsion Laboratory, which you see pictured on the right. Every day, a team of scientists and engineers uploading a detailed sequence of actions carefully planned for the rover to perform. This has been the typical way NASA has operated for several decades and missions in the past. While this has worked so far, it's definitely not scalable for some of the current present missions as well as the upcoming future missions for the next century. So why do we need AI? There's a growing need for future spacecraft to be autonomous, self-aware, and have the ability to make critical decisions on their own, like I said. This is primarily driven by two major factors. First is the difficulty with deep space communications. Apart from the fact that we are severely bandwidth limited, these planetary bodies are simply just very far, like you see on the slide deck here. The next few decades of space exploration is going to involve visiting the outer planets and their moons, like Jupiter's moon Europa, as shown on the right here. Now, for folks who don't know Europa, Europa is one of the most interesting places in our solar system. And the reason for that is it's the highest probability. We believe that Europa has the highest probability place where we can find evidence of life. It's an icy planet. It's an icy moon. So if you look at the picture, it's basically covered in ice, and we believe a few kilometers under the crust we have huge oceans, just like Earth. So what we are looking at is missions that could go to Europa and study the surface of Europa, maybe even dive down there. But now the challenge is sending a single signal to Europa and back can take several hours. So it's not feasible to teleoperate a robot when we are on Europa. The only way for us to make those missions possible is if those robots are completely autonomous and self-aware. The second reason is scalability. The image on the left here is a snapshot of all the satellites in orbit around Earth at any given time. And this is a few years old itself, with exponential growth happening every year. On the right, what you see is a vision of what Mars colony might look like, according to Elon. Now, imagine having a team of 100+ engineers and scientists sitting here on Earth controlling each of those assets. It does sound crazy, right? So it is. The only way we can scale up the space economy, which is a hugely booming economy right now, is if we make our space assets to be self-sustainable, and AI is a key ingredient in making that happen. Taking a step back, I am assuming a few assumptions here about terminologies and the technical depth of people. I've kept the presentation very high level, but if you have any questions that breaks the chain of your understanding, please do feel free to stop me. So how would AI-powered space exploration look like? To understand this, some of the work we've been doing in my group is to understand how these to map out a few key areas that planetary robotic missions could make an impact, where AI could make an impact. Uh, these are autonomous navigation, think self-driving cars on Mars, autonomous science and planning. I mentioned that we use a huge team of scientists and engineers to do our planning activities. And we use AI to do better mission operations, automated scheduling and planning. Precision landing. Now, I mentioned again about the challenges of landing on another planet. Think of an autopilot. So can we use AI to build an autopilot that will help our spacecraft land safely to its desired location? Autonomous manipulation, allowing our rovers to perform dexterous operations on this moon. We don't want it on other bodies, not just we don't want to just go to those surfaces. We want to actually do something useful there with our robots. So can we manipulate or accomplish actions like humans do with the same dexterity? And finally, successfully being able to work a long time alongside human astronauts for human robot missions upcoming in the upcoming decades. Said that, I would like to mention that in general, there's a wide range of applications in space exploration beyond robotics and autonomy, but that's beyond the scope of the work that I and my group does. We focus, and JPL as a general is a center within NASA that focuses on robotic exploration. So we really focus on planetary robotics work. And my work within that is to develop AI for planetary robotics. So this talk is really focused on that. Even more so, I would this I've been especially more involved in Mars exploration for the last 5 years across a range of different missions and technologies. So I would be focusing this up again on some of the work that we've been building on Mars exploration. Going back, I would be talking more in depth about giving you some examples of precision landing and autonomous navigation. I would not be talking much about the other three. I have done work on that, but if one of you are especially interested in it, please reach out to me later. Okay, so again, before we even say why Mars, this may be an obvious question, but we do get this a lot. So the main thing that we do at NASA is to answer 4 questions related to what you see on the left. We're really following the water, and water is a key to answering all of those questions. But whenever we build a mission to the Mars, our goal has been to answer these 4 questions. We want to look for life. We want to understand how the Martian climate is currently and in the past, and this would give us a lot about how Earth might evolve, or if we want to eventually move to Mars, then how would the climate be like, and how studying that, explore the geology of Mars. This would help us again understand not just about Mars, but the entire solar system and the universe, and answer questions about that. And most importantly, all of that work so that we can eventually prepare for human exploration. So in the right, you see some examples of interesting areas that we want to be going in the upcoming time, such as the North Polar ice caps, where we believe could be very high potential for human settlements, because there is a lot of frozen ice there, which could be mined into water. This is a snapshot of the current and future planned Mars missions, portfolio of those. On the bottom, you sort of see how those missions were designed, the main questions they were trying to answer. So when we first went to Mars, we were trying to follow the theme of follow the water. So we wanted to identify and even figure out if there was ever a water on Mars. I think we've had some recent great developments on that. We've made some great discoveries on that. And now we've been moving more towards exploring habitability. And more recently, we've started to very aggressively look for signs of life, past life on Mars, and eventually setting for human exploration. We are right now, you see already some of the missions have already landed on Mars. So the Mars 2020 rover and the helicopter, which I'll be talking more about. And the upcoming missions in the next decade, the highest priority target that we are working for till the 2030 is Mars sample return. And I'll very briefly, if time permits, get into that. That's been something I have been very strongly involved in for the last 3 to 4 years. As I got into JPL, I was working as a robotic architect. So I was looking over the whole robotics architecture of how robotics and AI could be useful in the Mars mission, in the Mars sample return mission. And that is a joint mission by the European Space Agency and NASA, and would be answering the biggest question we have for Mars right now. And it's very interesting because unlike a lot of science missions, that will be a mission which will be very heavily engineering focused, because we'll be building a lot of technologies so that we can bring back pieces of Mars to Earth and then do all the science here on Earth. So that's the highest space science target that we have for this decade. So let's start with talking about the latest rovers on Mars, the Perseverance rover. This is an image of the rover in the spacecraft assembly facility and clean room at JPL, where the rover was put together and brought to life. This is from last year in January, just before the rover development was complete, packed up, and sent to the Kennedy Space Center to be launched to Mars. The rover was launched to Mars middle of last year. It was a beautiful launch. Hope some of you saw it. It's a great feeling to see some of the work that we have developed and algorithms that we have built on our way to Mars. And it took a 7-month journey before it landed on Mars in February of this year. This was the first image that was transmitted back after it successfully landed. It was one of the most beautiful moments of my life, a highlight to see really the Mars rover that we worked on to some extent provided developed technologies to actually go and land on the surface of Mars. We had some really cool videos that were released in the media. I don't have those here, but if you do, just Google for the Mars 2020 landing and you should be able to find some really cool videos. And it's exciting because this is the first time we have actual footage of the landing. Any of the previous missions you might have seen were only simulations that you would see on the way down. So back to the same slide, let's start by talking about, so we talked about landing. So where does AI play a role and how does some of the computer vision, robotics, and machine and the other AI related work that we've been doing plays a role in that? So why do we even care? I briefly mentioned that landing is very important. I think any of you who's worked on robotics or drones or even interested remotely in space would be aware that landing on any other target body has traditionally been the most challenging aspect of any mission. This is where most missions fail. And this is one of the hardest things to really get right. And the reason is because we just don't understand those planetary bodies still. We have mapped them, we've been studying them for decades, but still we haven't done that enough that we know them at a centimeter level. And there's so many things that can go wrong in that steps that it's just very hard for humans to really plan out every sequence of things and they all go right. This is a great picture, motivating picture I like to share for the autonomous landing scenario. So this is from the Apollo missions in the 60s. And what you see here is the Apollo lander. And this was, if you look very closely, one of the legs is sitting on this kind of like a rock. And the overall tilt of the lander is 11 degrees. And it is only 1 degree off from its margins to actually topple off. So if it was 1 degree off and it landed on another rock piece, which was a bit taller, it would not be able, the astronauts would not be able to come back. And we would have basically fatalities and a lost mission. So it's been a really big challenge for any missions we've been developing so far. You might have heard about this same scenario more in the context of SpaceX and the relanding that was done, a lot of the great technology that were being developed at NASA JPL, and then originally for the Moon and Mars that were also worked along with SpaceX. So some of my ex-colleagues did end up going to SpaceX and they worked a lot of the technology we've been developing at JPL for 15 years, transmitted, and they led up the team that worked on the relanding for the SpaceX rocket. So that was, again, great to see some of the commercial tech transfer of this happening. On the JPL side, we've been focusing on developing and perfecting that technology, enhancing the state of the art for autonomous landing on Mars 2020. And this was the first time advanced autonomous computer vision was used on the surface of Mars, for making this critical. And this was one of the most key technologies that we developed. And I'll talk about this in one slide, but first I wanted to talk about where we landed. So the Mars 2020 landing site was the Jezero crater. On the top, what you see are pictures of what Jezero crater might have looked like in the past, where we believe that it was a delta, which would have led to, which make us believe that it is one of the most interesting places that we can probably find signs of life or evidence of past life. If you think about the places here on Earth which serve as these deltas, they are some of the most biodiverse, rich places to study the planet. And this is the same applied for other planetary bodies. And this is why we want to be going to those areas. On the bottom, what you see is orbital images of what the Jezero crater looks like today. And even just a single snapshot clearly shows you that you can have these delta areas, you can see that you have these river channels that are flowing, and this really comes out into this delta and opens it up. So it's a really gorgeous location on Mars that is very interesting from a science perspective. The only challenge being that because of its amazing terrain, it is also very hard for us to go. Historically, we've landed on Mars in areas which have been easier to get to. On the left, what you see is uh, something called a landing ellipse. So when we send a rover to Mars, based on the technology it has for landing, it has a landing ellipse, and that is determined by the uncertainty of how much area we can land on. And the biggest ellipse you see is for the Mars Pathfinder, which was sent some time back, and you can see that it can only land and have accuracy of hundreds of kilometers. So if we send that rover, we have a very high chance that we might land somewhere where we would not be able to land safely. So if we wanted to land at Jezero crater, we had to be extremely accurate, and we had to bring down the ellipse from that gigantic ellipse outside to the small circle that you see in the middle. And that was made possible by computer vision technology. And this is one of the first real world, maybe out of this world, uses of computer vision and development of AI enabling something as huge as this. So this has been really a huge milestone in the history of computer vision as a whole, and we were very lucky to be part of that. So on the right is a single snapshot of how we made that work. It's a system we call landing vision system that uses aspects of computer vision like feature tracking and image mapping, as well as something we call map matching. So what it does is as you're going down, it tracks images as well as takes images and maps those to orbital maps to localize itself. So we are solving a localization problem. To going a bit one second deeper into it, the reason why we need this is the uncertainty that you see on the left comes because when we are flying down, there is a lot of error that builds up. You have you're when you're flying, you basically you are deviating a lot. There is a lot of factors that play into account that throws off the accuracy that we have. And so IMU drift is one example of that. And this is where we use AI and localization to correct itself. These are some actual images from the software while it was running for the 10 seconds that we deployed the computer vision software while it was descending on Mars. There's, again, some cool videos of this on YouTube. There were some enthusiasts who actually reconstructed a lot of the landing. So great citizen science work from some people. And this is really exciting to see some of that work. But this is, again, you can see these green patches. Those were actual features that were being extracted. We were matching them to pre-mapped orbital images to localize where we are on the surface of Mars when we are landing. And then using that, we can identify where to go to. So on the left, you see the green dot is where we actually ended up landing. So at around, I'm forgetting the exact number, but at X number of X kilometers above the altitude, it runs that algorithm, and then it locks into where it thinks it currently is. Based on this, it queries the hazard map. So on the right is what you see is the hazard map. So all the areas in red is where we cannot land. So if we landed on any red area, we would have basically crashed and the mission would have failed. So once it localizes itself, it has a much better certainty of where it is, and it tries to, and it autonomously in a few seconds, it finds, okay, this is where I can get to with this much error margin, and this where it goes. And the actual errors were really low. So we landed within 5 meters of where we wanted it to land, which was amazing. So there was a really nice comparison I saw. It was something in the order of like, imagine playing golf and doing a hole in one where you're throwing it off for several million miles. So it was really great to see such perfection and this technology working with such almost fluency. This is an orbital image that was taken later after the landing that shows images of where it was. You can see Perseverance as a couple of dots. There was the descent stage. I'm not going into technical details of how the different stages of EDL works. EDL stands for entry, descent, and landing. So again, I only focus on showing some pictures of where computer vision and AI were used to make this happen. These are images after we landed. So if you see on the right, top right image, that's the ellipse. Again, that's the landing ellipse. The blue dot is where we landed. The white lines are showing the first few images, the panorama made from the first few images after we landed on Mars. So if you carefully observe towards the left field of view, you would see a notch in the orbital image. And that's the notch that's been enlarged on the left top left image. And you can see that. So again, great to see picture perfect landing and having computer vision enabled this kind of ability so that we can land somewhere that's that interesting for science. This is some of the pictures from the operations that was done after. So what you see is from the white dot, these are some planned trajectories to how we plan to explore how the Mars 2020 rover, which is now called Perseverance, the Perseverance rover will be exploring the surface of Mars. The reason we have these two trajectories are from the white dot, we have the region just left to the white dot is a very sandy area, so we cannot actually explore or drive over that. It's not feasible for the rover to drive. So the engineers have identified these two areas that it's going to go around, pick one of those and do some science on its way to eventually finding its way to the mouth of the delta and then explore the area within. So that's the roughly planned trajectory that we have and we'll be exploring in the years ahead. So we saw how computer vision enabled precision landing. Some of the work that I am currently doing after that, I split my time dividing myself between doing research and future technology development for 50% of the time and doing contributions to current missions where a lot of the technologies and research we are building in AI can be applied to missions. So some of the work we are currently looking at is far-fetched. So how can we now that we have landed on Mars so accurately, how can we go to more difficult bodies and enable that even more precision accuracy? So a couple of things we are looking at in precision landing, if people are interested, is exploring other planetary bodies like Titan or Venus, which have a lot of atmosphere. So right now we did this for areas where we could see the surface. Now, if you cannot see the surface, how do you do this? That's like trying to fly in a foggy environment. So we are trying to work with how to work in those difficult environments and trying to think this from a physics-based point of view and trying to do AI using a physics-based grounding. Another area that I'm heavily involved in is using more and more machine learning and reinforcement learning. The place that comes into interesting is once we want to go and land into new areas. So right now I showed you some examples of where we landed in places that we have at least orbital maps from. So let's say you want to go and land in an area which is completely new. How do you land there? So that's where we're exploring concepts of reinforcement learning and transfer learning to see how can we go and land reliably, completely autonomously and reliably in new areas. So after precision landing, let's switch to autonomous navigation. We showed the trajectory that the Mars rover will be taking in the previous image. So this is a very challenging path. And one of the things that we really want to focus is autonomous driving. So self-driving cars on Mars. For the Mars 2020, the Perseverance rover, we've been developing a technology called ENAV, which stands for Enhanced Navigation. So we did have some very brief amounts of autonomy on the Curiosity rover. So it does have an AutoNav, which stands for Autonomous Navigation mode on the Curiosity rover, but it was briefly used and it was only a technology demonstration. The enhanced autonomous navigation will be on the Mars, will be much more significantly used on the Perseverance rover. So we already have self-driving cars running on Mars. It's obviously a different environment, a lot of different challenges. In some ways, it's very easy. You don't have to deal with pedestrians and other issues, but you have to deal with reliability because one wrong issue and you have lost a $5 billion rover. So that's really, it's more of high stakes, and that's where a lot of different challenges from risk and reliability come into place. Now, if some of you observe that video carefully, one thing, so this video was from the Mars Yard at JPL. This is where we try to reconstruct some of the Martian terrain. So to a naive eye, this picture would look like rocks that are just randomly spread out. But what we have is world experts in geology who have studied Mars, and they try to perfectly reconstruct the exact distribution of rocks and how the surface and the soil should be on Mars. And we try to recreate those environments in as perfect scenario as we can here on Earth and do a lot of that testing. But so what I was saying was, from an AI perspective, if some of you carefully notice, this video was sped up 50 times, and that's the key where we have issues, is that the Mars rover currently is really, really, really slow. Uh, Almost so much that I was surprised that it moves so slow it's boring. If you do it, see it testing, it moves only at centimeters per second, and in the past, it was really limited sometimes by mechanical limits. So we just did not have radiation hardened motors that could run fast enough. But recently, the problem has also been computation. We do not have algorithms that can run as fast on those systems. And that has been a huge bottleneck because we do want to go faster so that we can traverse longer. So one of the main challenges that me and my team are looking into is how to solve the autonomous navigation problem on planetary robotics. So how can we drive safer, faster, and further? And we truly believe that it is more of an AI issue than a mechanical issue, because this is an example of the lunar rover, a lunar roving vehicle from the Apollo missions. And this used to drive almost 100 times faster than the Curiosity rover can. Now, again, before any of you jumps to the conclusion, obviously we understand that Moon is very different from Mars, uh, but it's also that a lot of that was made true because we had a human brain behind it, and the algorithms were not slowing it down. So and this is a huge thing we're solving, and this is one of the biggest areas we've been doing research into. And the reason for that is that any future missions will involve very long range driving. So far, we've been driving only short distances, but we want to be driving significantly further distances in the order of hundreds or thousands of kilometers. We are looking at missions. So imagine 10 or 50 years from now when we have human missions going on. We also need an entire infrastructure for how we can support those missions. So on the right is example of one of the mission concepts we are studying is of a water transporter. So we want to land humans on the moon, on Mars, but we want to probably land them on somewhere in the equatorial regions because they are more friendly from a climate perspective and a survivability perspective. But then most of the water lies on the poles. So can we imagine a mission where we have robots that go from the equator to the poles and basically serve as water transporters? So missions like this would require autonomous driving, almost in an industrial fashion for thousands of kilometers. Can we do that with current technology? Is something that we are looking into. So how do we actually do navigation on Mars so far? And what are the kinds of things we're developing? For more than for 2 decades, we've been proudly operating rovers on Mars, as we've seen. As I mentioned, our topmost priority is safety. The current version we do this is very human in the loop. So we have some limited forms of autonomy, but at the same time, at the end of every day, which is a Mars day, which is called as a sol, the rover transmits back images and panoramas of its current location. We use 3D software here on Earth to reconstruct that area, and then scientists and planners plan out a detailed sequence of events, like I said, and trajectories for it to map out. It does do the navigation on its own, but a lot of the planning activity happens here. So the human brain really does a lot of the reasoning behind safety. Now, and a lot of that is done through intuition. So some of that is geometric. We use geometric features like, are there brake obstacles in front of you? But a lot of that is also semantic, like I like to call, and they are things like, is that a solid surface? Is that a hard surface? And if you think about when you walk or you drive, you do a lot of that reasoning on your own. Now, for folks who are already working in AI, this might sound very straightforward, and this is something we also do a lot in self-driving cars. So we used to do, for Mars, we used to do, the autonomy that we have is using geometric features. So we've been doing classical computer vision to analyze the terrain, look at the terrain maps, look at elevation maps, and try to map out where we can traverse. But what it can't do is do reason for things like, is there sand? And this is one of the most challenging issues for rovers driving on Mars. We have lost already a rover, the Spirit rover. The Curiosity rover was stuck for several months. We had significant damage to the wheels because it was really hard for their planners to figure out that we are going to be driving in these really rough areas, that sandy areas and rough areas where we might damage our vehicle or lose it or get it stuck. So this has been a major challenge and a request for people like us who want to be developing technologies to solve this, they've been requesting that can we do this autonomously? Can we solve this? So this is where some of the work, one of the work that I was involved in the last couple of years was to develop a deep learning based technology that can do terrain classification for Mars rovers. We call it Spock. With it may or may not have reference to some characters, but yeah. So what it does is we've adopted some of the deep learning technologies to build a ability so that it can do the semantic reasonings while it's traversing autonomously. So we have two versions of it. One does this from an orbital map, like you see on the right, and one it does it from the rover perspective, like you see on the left. And as it's driving, it's reconstructing not just geometric features, but also, sorry for that, it's also labeling these images using some machine learning technologies that we've been developing. Uh, and it reasons then using this to avoid areas which might be highly probable of sand or areas which are dangerous for it to do. In terms of the actual research and technology development, again, I'm going to go at a very high level on this, but we've been not doing this from the ground up because there's no need to do this. There's been so much development on deep learning, machine learning in research and in academic community. We've been building on that revolution. But the main thing we've been doing is adapting that to our challenges. Now, if any of you have worked on any real world problem with machine learning, you would understand that most of the algorithms that works on benchmarks don't really translate when you start applying it to data set. Folks from project managers would probably have really good understanding of this by, okay, you pick up this paper, but it doesn't really work on technology. When you put on this on a self-driving car, it's a totally different beast. And that's the reason it's been 30 years already, 30 plus years since we had the first self-driving car technology coming up, and still we are still finding a challenge, and we don't know how far it's going to take for us to develop. So doing this reliably is a huge challenge, and applying this to space missions brings its own challenges, like you see on the left, on the right. We have huge challenges with data. So we're very limited on what kinds of data we have. Definitely don't have limited label data, so we cannot train on cats and dogs to train a terrain classifier on Mars. We have limited onboard capability, like I was talking about. So just for reference, uh, the current onboard computer on the Curiosity rover and the Perseverance rover has 1,000th the ability of your iPhone. So it runs an old PowerPC grade computer, and it does have. So one of the another key developments that we did for the Mars Perseverance rover was an FPGA. So it does have a computer vision accelerator, and that was developed specially to overcome this issue. But that's something where we run the visual odometry and the visual localization algorithms, but not it's not available. We don't have capability to deploy machine learning on FPGAs yet for the Mars rover, but that's something we've been building. A lot of my research is also involved into looking at modern um, different avionics options, like can we use edge TPUs, can we use spiking neural networks, can we use a lot of different new advancements in computer vision, in hardware, AI accelerators and hardware, and can we deploy some of that and deploy our um, algorithms on those things, and can we make them robust enough to work in space? Another thing one of the challenges we face, again related to, is system validation. So this is very unique to space to some extent, and may apply to some of other mission critical systems like aerospace, is you cannot really have an agile iterative development process like a lot of the other industries have. We have a single shot to get this right. So the only way we can do this and convince the stakeholders that we can actually deploy and build AI is to do extreme system validation. This is obviously challenging because AI and machine learning by itself is not very explainable. So this is another very new area of research that me and my team are looking into, is how can we uh, do extreme system validation and provide guarantees, not just from a theoretical perspective, but from an applied perspective. I'm not going to go into details. I had a few more slides, but since we're short on time, I'm going to skip a few slides on these of what we've been building. Maybe this is something I can show quickly. So one thing to overcome data that we've been looking into is use a lot of the development in computer graphics, working with some of the AI startups to build very high photorealistic labeling softwares that we can use and deploy and train data with. Very quickly, so this is some testing we did on the Curiosity rover images of deploying deep learning on it. And you can see some examples of this. We still haven't uh, done this for the Perseverance rover, at least not in the extensive way where we have results to show. I'm gonna skip this, skip this. This was again showing where we're working on different kinds of hardwares. Uh, This is again like this is a slide to show talk about. Sorry if I'm running fast on this. I can come back to this later if some of you are interested. But this is some videos of uh, testing that we've been doing, and this is something we did a few months ago, where we've been now doing very long range drive tests. So this is a region behind JPL where we've been taking the algorithms, validating them, running them for kilometers and kilometers for multiple days, and testing the extent of how well those algorithms perform. We studying those breaking points, and that's what we've been doing. Uh, this is, and the second thing we've been developing is on the path planning side. So as I mentioned, that our algorithms are really slow. So one way to accelerate that is to remove the human from the loop, and that's what we are trying to do with the deep learning based terrain classifier. The second is just advancing more of the path planning itself. This is the architecture for what the current Perseverance rover has. Uh, a very high snapshot of path planning for folks who might have interest in this, might have studied a bit of how motion planning works, but I'm not sure what's the background of all the audience. I'm not going to go into details. But the way it works is we have three segments of it. We have a global planner that tries to estimate where to go on a long range drive. We have a local planner that looks at the near proximity of the rover to plan out how to make a near trajectory. And then we have something called a ACE check, which looks for collision. So that is the most expensive part of the algorithm. Now, if you imagine to verify every 3D point around you, and if you want to make sure that you're not colliding into something, it very quickly becomes a combinatorial optimization problem, which is exponentially huge. Now, if you have to do that in a brute force way, this is where it really slows down the algorithms to the point where currently the Perseverance rover would take almost 5 to 7 seconds after each point to think about the next step. And this is where it becomes more of a drive, stop, think, drive, stop, think. And what we want to do is change that to a drive as you think. So it's driving and it doesn't have to stop, and it can do that processing in parallel. And this is where we've been also doing some research on using machine learning and reinforcement learning to, ho- to to realize that how can we get this human intuition to be part of the planning problem. So if you look at the picture on the left, what we have is something that a human would do. You'd look at that image and very easily you would have, okay, let's go to the right. It just makes sense. But our current rover does not have that capability to do that from an intuitive perspective. It will exhaustively look at all those arcs and work on it. So the question we had, so this was a summer project we were working on last summer. And the question we were asking was, can we internalize that kind of intuition into the path planning architecture itself? And this is where we developed, again, a machine learning technique to do extensive simulation of rovers. So what we did was we tried to leverage imitation learning, and we collected a lot of data, both in simulation as well as through past data of what the humans have been training our robots to be doing. And we used that intuition to train a neural network that could allow us to predict that kind of intuition. On the bottom right is you see different kinds of terrain that we were working on and developing a model for that. And we haven't deployed this on Mars. This is still research, and we're still working on it. But we really hope to deploy this in the next year, where we want to do maybe a tech demo of deploying this technology on the Mars rover, so that we can, and this would accelerate through simulation and analysis. We have shown that this could accelerate our planning time by 5 times. So this would allow us to go from 200 meters per day driving to almost a kilometer of driving every day. Now, fun fact, this is something very close to almost a glory moment for Project Manas and Manipal, is because one of my students who worked on this was a senior of yours. He's a fourth year. His name is Siddharth Venkatraman. He did work on this. He was an intern with us last year. And last summer, he worked on this technology that we hope to deploy to Mars next year. So again, great work by him. One of the brightest guys I've worked with. So yeah, again, some some influence of Project Manas here, making its way to Mars, hopefully someday soon. This is a single picture image of what my vision for future Mars rovers look like with complete AI in the thing. We want to build something like a Google map on Mars where Mars rovers can query and do long range driving. I know I'm going a bit over time on this, but I'll try to quickly go over some of the other quick things and then we can move to question and I have some flexibility to go over time after that if you guys are fine. So I've talked so far about the Mars rovers, but another very key areas of autonomous navigation that we've been deploying, and most exciting part for me, is the Mars helicopter. I was very fortunate, having worked a lot on drones through my undergrad and through my master's work. I was very fortunate to have been part of the Mars helicopter mission. It's one of the coolest things, I believe, that has ever been developed at not just at NASA, but across in engineering in general. We were able to achieve the first. So this is an image of the Mars helicopter, again, from the clean room. This slide should not have been there. Okay, this was just a teaser video of the Mars helicopter and what it was supposed to be doing. So Mars helicopter is the Ingenuity helicopter is supposed to be a tech demonstration. So it's not going to be doing any science per se, but the main goal was to show that we can achieve powered flight on another planetary body, especially on Mars for the first time. This is something that is believed is not possible for centuries, and we have the team at JPL were able to develop and demonstrate this that we could achieve powered flight on another planet. And again, one key aspect of this was the ability to do computer vision on it, because the only way we can fly this is if it does its control and localization on its own. As you see in the video right now, this is the part that it does its computer vision, where as it's flying, it takes images of the surface, it tracks those over time to localize itself. It's a very popular technique for robotic researchers along the lines of visual odometry and SLAM that we use. This is some video images of testing we were doing before the Mars helicopter to validate the algorithms. You can see that as it's flying, it's taking these features that we call tracking those features over time to localize itself. This is some images from when the Mars helicopter was dropped off from the belly pad of the Mars rover, showing the airfield where we have been operating, as well as some of the initial maps. Now, I believe, this is one of the coolest things I have personally to share with and brag about, is the first video of powered flight on another planet. I hope some of you have seen this already, but if not, I do request go out and check out some of the work we've been doing in the videos that have come up from the Mars helicopter of developing autonomous drones, some of the first key localization algorithms for the autonomous drone, and then having them deployed to Mars and doing the full circle of being part of the team that developed the first computer vision algorithm. I think this has been a very fortunate journey, fortunate blessing to be part of the journey. This is the flight log we have from so far. So we've had one more flight after. So we've been having, it was supposed to be a tech demo for 5 flights, but it was a exceptionally overwhelmingly successful mission, and it surpassed anything we believed the Ingenuity helicopter could do. And the whole team decided that we would extend out the mission and do even more flights, and with every flight we would keep pushing the boundaries of what could be achieved with the helicopter. So with the recent flights, we have been really pushing very far distances, and we never believed we could even do more than 20-meter distance. It was really the baseline to call this a success was to do 3 takeoffs and landing. That's it. That was what we designed the helicopter to do, but we've really surpassed it. And it's amazing that the algorithms really worked through it with only one glitch we had in one of the flights, except that, and that was also not an algorithmic glitch, but more from a acquisition perspective where the frames did not come through. Okay, trying to wrap up very quickly. Future missions, we've just not been developing missions for right now. A lot of my work involves for how can we develop AI for future missions. And one of the coolest aspects of my job, I feel, is to be part of developing algorithms for really unique hardware robots. So these are some examples of robots we've been working with for very extreme environments. So on the left is, on the on the center is what we call the lemur robot. It's a rock climbing robot. For future missions, when we go to Mars, what the scientists really want is so that we can go to the surface, climb on the surface, and do science by sampling on those surfaces. On the left is a version of RoboSimian, which was so RoboSimian is a robot that was developed for the DARPA Robotics Challenge a few years ago, and that was JPL's entry into the DARPA Robotics Challenge. And we have since then modified the RoboSimian to work for different extreme environments like Europa. So on the left and on the right are examples of what we are developing, a version of RoboSimian that could someday go to the surface of Europa and explore the underground oceans. So the kind of activities it had to do is do navigation on ice. So once it lands, it will have to do autonomous navigation on ice. So we've been developing different mobility systems and AI technologies to develop and allow it to navigate on ice. We develop those software, then we go to places like the Greenland, Arctic, Antarctica, and then we do those testing in those representative environments. Part of that mission would also be about diving deep into the ocean. So that's where we are developing technologies like you see on the left, which we call aquasimian, which would go deep down into the ocean and then be able to do dexterous operations. And this is a version of this also applies to here on Earth, where we could do some testing for things like for oil and gas industries, where this could be used for maintenance or for disaster response, like could be used for the MH370 case or other aircraft disasters which might have water landings. So we've been looking at those. We do a lot of field testing. That's one thing very unique to us. We develop algorithms, we go out in the field, we test them. So this is a moon cave we found. I mean, sorry, not a moon cave. On the top right is what you see is a picture of a moon cave. We found an underground cave in New Mexico in the US, and we believe it's very similar to what we call as a lava tube or a lunar cave. And so we went there, we took our lemur robot and we did some testing. This is an example of some of the computer vision technology we've been developing, where we want to now, rather than reasoning on where to traverse or where to navigate, we're like where to climb. So this is any area in green is where the robot can hold a grip and not fall. Any area in red is where it would, if it holds a grip, it's not good enough that it'll be able to hold a grasp. So we've been training machine learning algorithms to can do that. I will close with this video of our testing that we did with the lemur robot in the New Mexico cave. And the last slide, I'll skip over all of this stuff, don't have time. Lastly, I would say I think a lot of the work now we're doing is towards human exploration. So this is something I personally am very interested in. I'm a robotics engineer by training, but I'm very, very excited about the idea of humans going to Moon, Mars, and beyond. So personally, I'm starting to work a lot towards how can robotics play a major role in enabling this human explorations in the decades coming through. Thank you. We're always looking for really great people to work. If any of you are interested in space, want to nerd out on robotics, space robotics, please reach out to me. We're always looking for really excellent people to work with us. So feel free to reach out to me. You can write to me on this email ID. I can also send this in the chat, but I'll stop there heavily over time. So I'm going to stop and take questions. Thank you guys for listening patiently.
Thank you, Shreyansh, for the presentation. It was really insightful towards the usage of AI in robotics right now in the present scenario. And depending on how much time would you have for answering questions right now?
I can have half an hour at least, yeah.
So you've worked extensively on sample collection and return. You mentioned in your introduction as well. So what was the role of AI and robotics in that? If you could elaborate on that.
Right. That was the last segment of my slide deck that I could not go through. But yeah, if you maybe to answer that question, let me quickly share it just to show it. I think it'll be easier to show it with that.
Yes.
Sure. If you guys can see my screen. So something we've been developing for sampling is, so one of the, as I had mentioned at the beginning of the talk, one of the main missions that we are working towards for the rest of the decade and 2030 is Mars sample return. It's an entire campaign that's going to be part of 3 missions. So Mars 2020 is the first part of the mission, so our goal for Mars sample return is to bring pieces of Mars back to Earth. And this is a very challenging problem because it needs a lot of different missions to work together, as well as us to do a lot of things we've never done. The first part of that mission is collecting samples on Mars. So this is where the Mars Perseverance rover will be collecting samples of Mars and putting them in the sample tubes and dropping them on the surface of Mars like breadcrumbs. Now, the first sample actually will be collected this week. I think we have mapped out where we are going to be collecting surface. So we are right now planning to collect our first sample, put them in a tube, and drop them on the surface of Mars. When we do get to, so this is what the Mars Perseverance rover will be doing throughout its mission. Then we have a future mission, which will be the sample return lander. So this is the Mars sample return architecture as a whole. So you see we have the Mars 2020 mission, which will be dropping samples. Then we will have another mission that will go and collect those samples. We will have a third mission that will basically deploy this into orbit and bring it back to Earth. There was a fun cartoon video in the next slide, so I'm going to just let this play. So this is what the current Mars 2020 rover will be doing. It will be collecting the samples, splitting them in the tube, and just dropping them on the surface, like I said. So this would be the second mission, and it would then put them in a MAV and then take it into orbit. So as you see in that, if you're a robotics person, you would see there is so many things that needs to happen all autonomously, all aspects of it. Collecting, we've never done autonomous operations to the point, even right now, if you know about the Amazon picking up challenge, or if you're into robotics, picking up anything is a very hard thing for robots to do right now. Humans do it so easily, but manipulation is one of the hardest problems that we still haven't solved in robotics research. And doing this autonomously on Mars is a huge challenge. The way we like to picture the problem is, for the next rover, imagine sending it to one of the deserts, Death Valley, if you guys are aware, or Sahara Desert with a 100-kilometer radius, where there are 20, 30 tubes spread across. And the goal is to find those tubes, pick it up on its own, bring back to the lander, put them in a mission. The second part, so all of that is one of the most challenging problems that autonomous robotics has had to face. And this is where I think doing a lot of the sample collection and sample acquisition plays into part to answer your question. This is again a video of what it might look like from a cartoon simulation. So we've been developing technologies that could allow us to very precisely, and to give you a sense of why this is hard, uh, the precision that you need to pick up those tubes is the order of 2 millimeters. So you need to have accurate detections of where those tubes are within a matter of 2 millimeters, or you cannot pick it up, because that's the precision. So it's really not just developing technology for it, but making it so robust, accurate, and precise enough that you can accomplish your task on another planet. So that's what we are looking on from that perspective.
That's pretty cool. That the entire presentation, the word I can come up with is cool, if I'm being honest.
Thank you.
And so I'll just one more technical question before we move on to your journey and all those things. Is that a little bit of a personal question, as well as somebody had put this up, is that you spoke about the lack of computational power. You spoke about the lack of data sets because there's only so much information you've gotten from past missions. And you said that the power or the computational power which you have is not even close to what we have in our cell phones. So now what, maybe this is for the people maybe who are a little versed with deep learning, machine learning. So what are the technical tools do you use to deal with the scarcity of data as well as scarcity of computational power?
Right. So there's something, I mean, it's a very ongoing process. We are learning as well. This is a very basic research problem because most of the industry has not dealt with it. I could not go into detail. It was hard to go deep into some topics as well as go broad. And I'm sorry if I could not go into some of the details for that. But so something that I'm personally very excited to and looking at is self-supervised learning. I think there is a lot of aspects, like obviously we have supervised learning is to some extent considered solved from the perspective of if you have a huge training data and the same distribution, you can just train a data to really fit that distribution. But unsupervised learning and self-supervised learning is really not looked into much. Part of it is just because a lot of people just hasn't have to deal with it. Like a lot of the problems where the money is right now is being solved is where you can. There is a lot of data available, so it's easy. People are just trying to work with it. It just makes life easy. So then most of the people who are working on machine learning still don't understand deploying it on robots and what are the challenges come with actually deploying and making it work on a robot. So the machine learning community does not work with robotics community. So one of the biggest even things we look at and where JPL comes at expertise is this agile process, which is not just developing a software, deploying it, but testing it on hardware, learning from that, and then modifying our algorithms for it. So to answer, to go more specific to your question, for tools that we look into, so we've been looking at unsupervised and self-supervised technologies for trying to come up with data. We've been looking at advancing our simulation capabilities. So we've been looking at sim to real capabilities. How can we come up with highly photorealistic simulation and labeling softwares? Uh, One way we are looking at is how do you rethink models? So, I mean, how do you do model compression? How do you really go from you? Do you really need a gigantic network? So, there are some unique aspects to our challenges. Let's say you want to detect sample tubes. You are not trying to solve the general AI problem. You don't need to detect cats and dogs and tables and chairs and everything. You're given one thing and you need to detect that. And mostly that's what happens in any engineering real world problem. You see papers, they're trying to solve the general problem. But that's not what happens when you go and want to apply it to a real product. So you're given this task. Okay, let's say you want to build a home product. You want to detect your keys, your things, 5 items you want to detect. So you already have so much prior knowledge. You know what that looks like. You know what all of that. So now you suddenly don't need so much data. So this idea of how do you combine model-based reasoning, so you have so much domain knowledge and you have some amount of representation power from deep learning. So how do you combine them together? So we look at that. How do you build so that sort of like leeways into hardware is hardware is more of a challenge, definitely, but we've been lucky that there's been lots of development happening on the field too. Um, Unfortunately, there is no economy for a GPU in space, so we don't have an equivalent of an NVIDIA. So it could take millions of dollars to produce a single GPU. It would have taken that years ago, but then once you have a commercial economy, then that brings down the price. That's the challenge why development takes so much time. But there were also things where NASA was traditionally very risk averse, and it is risk averse. I mean, you're working with billions of dollars of uh, taxpayer money, so you have to be risk averse. You cannot just deploy something without money. So it was very risk averse in that sense. But Mars helicopter and the Ingenuity helicopter is a great idea of that. So when we were thinking about 2 to 3 years ago, when we were studying on the books of Mars helicopter, the problem was we had an upper mass limit just because the Martian atmosphere is so thin, you can't fly. So there is just no way for you to bring up your mass. Your mass has to be really limited. And what that came down is it was like 10 to 12 grams is what you have to use your computer board. That's it. You cannot have. So now imagine having your entire computer only weigh 10 grams. There's hardly anything out there that does that. So we tried to find out, and we were lucky that we had a few people that we were working with, some other projects that we were using. So for some of the army projects like I was involved in, we were developing the army was interested in developing very micro UAVs. So we were developing very micro UAVs that could fly and do surveillance operations. And we were starting to look into the Qualcomm Snapdragon processor for that because it's the same that's used in your phone. uh, but we didn't think that it could fly to space. But then we reached out to the Qualcomm folks and we realized that they had actually done radiation testing on that. It's just that they never put them in the data sheet. So, and then we talked to them, we realized that it just has enough power, enough radiation qualification that it could survive the small amount of time it needs for Mars helicopter, and that gives us enough power. Now the challenge was how do you develop our algorithms to work on the Snapdragon? So it's a constant process. of trying to find the hardware, making it work for space, adapting your algorithms to work on it. Uh, and to answer, again, this goes back to the data problem. For most of the good engineering products, you still don't really need extensive deep learning to work. This is something I have been learning a lot. I mean, I come from the computer science side, so again, I'm an AI person, so it's my day job to try to make AI work and like push for AI, be evangelist for it. But I learned that for a lot of things, you can actually use very simple algorithms that work extensively well. So a good example of that is I have had a few discussions in the past with Project Manus folks, and they have struggled with localization and developing their visual odometry algorithms, trying to use deep learning, trying to use machine learning. On the Mars rover, on an unknown planet where we didn't know anything, we've been running visual odometry for 12 years with almost no failures. We've had only 15 attempts where it failed. It's a simple algorithm. You don't need to change it. So it's how do you use, but make it robust enough to work in really good scenarios. So summarizing, how can you nicely use a lot of knowledge and prior information you have, the model base, how can you use self-supervised learning, unsupervised learning, extract a lot of representation power without necessarily needing labels? How can you adapt your algorithms to new hardware? So one thing I'm personally very interested in is adapting neural networks to FPGAs because they are very low power settings. You can deploy a lot of things. So we've been having some research on that end. So there's no magic bullet to it. It's sort of like an agile process, but a lot of like looking at picking up technologies and then looking at what works.
Okay, that's great. So, yeah, that's very interesting. And yeah, I think a lot of the AI people struggle with this problem where the solution is okay, run it on a GPU or run it on a TPU
Right,
and throw more data at it. So that has been the outlook there has been till now. So that's very interesting.
right.
Okay, so we
And
can move on to some.
one
Yeah.
one aspect, just want to throw it on. One aspect that people don't, especially when it comes to AI and machine learning, which is the biggest open challenge, we still don't know how to solve it. We're still learning is safety. I mean, AIs are non-explainable, and there is no guarantees. So I don't think anybody. I mean, if anybody in this in this audience is aware of formal verification, it's a field of computer science that deals with providing formal guarantees. That's something that people have been for 50 years using to guarantee systems. So anything from aircraft you fly to space, any mission critical system or missile technology, anything which is super mission critical has to go through a formal verification process. The basic foundations of formal verification breaks when you think put deep learning into it. So it's a very new field which is basically coming up with how do you do assurable deep learning. So how do you assure systems? How do you do verifiable machine learning? So it's something we are starting to look into. So there's a lot of areas, and it's really starting off on how do you apply these things to space or any mission critical system.
That's fascinating. Okay, Shivansh, I think you can ask some of the other questions which people have, some of the non-technical questions.
Yeah, I saw a few more technical questions piling up, but I think we're running short on time, so I think we'll move on to the non-technical side for now. And I think the one main question a lot of people in the audience are curious about is your journey from Manipal to NASA.
Right. I'm curious if there's any more specific questions about. I mean,
Yeah,
I
so
can
like,
blabber
can
about
I?
this.
Yeah,
I can
So,
blabber about this for hours. So like, yeah,
yeah.
it
So if I
might
can
might
add
be
on to
useful to
that
have.
question, yeah, if I can add on to that question, like everybody does some projects in their undergrad days, and some of them lead to careers. Some of them are just maybe they end up in something like, okay, if I'm being blatant about it, then a certificate or an LOR or something like that, which doesn't have, let's say, long-lasting repercussions on your career per se. But when I personally was going through, let's say, a LinkedIn profile or something like that, so everything felt like it connected. So did that
Yeah.
just happen, or was that a conscious thing? Or if you can just even like tell us about few of the milestones which, looking back, you felt were important
Right.
projects.
Right. So it does connect very well, but it always does looking back. I mean, like the famous Steve Jobs line, it always connects back looking back. I have been fortunate. I mean, part of it was just conscious decisions I was making, but I was just as lost as most of you would be in your careers. I mean, that never ends. Just to be like, I'm still feeling lost in what I want to do next. So you always feel that no matter where you are. So embrace it, But there's a few things that you can do to make it work. So you mentioned about things that build up and things that are for certificates. I think that's where you need good clarity on what you're investing your time in. Uh, you need good mentors. I was very fortunate. So I guess let's just say that's where. So, okay, the first thing starts with your interest. It's okay to have multiple interests. It's okay to like try around a few things, but at some point you'll really need to go deep. Uh, you can always start late, but if you start on your fourth year, hoping that, okay, now I'm going to start in robotics and then get there, or start in another field and get there, you'll get there, but you'll just have to take more time. You're not going to get there by 1 year. You cannot do in 1 year what somebody else would be doing in 4 years. It's not feasible. Um, so find something you're interested in and go deep into it. So one thing that really helped and connects for me is I got into robotics and I went all the way in. So it's like basically I kept going deep, 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 deep. That really helps it, because I mean that builds your profile. That is something I would, I mean, if I'm looking for somebody, that's what I look for. Like how much focus. Like if I so define your interest, go deep in it, learn more about it. There are, I mean, right now I would say you guys have a lot more opportunities for folks in robotics to do it. I mean, when I was starting off, there was literally nothing on lab that was doing robotics. There was very brief things that were happening. I mean, Robo Manipal probably, I think one of my colleagues had started Robo Manipal on the side. So there was hardly any robotics happening there. I mean, we still had some line follower challenges and stuff like that that was happening, and there was few, but there was again in first year pretty much nothing. I had opportunity to so getting. Thankfully, I was connect. I found robotics and I tried to learn a lot on my own. But right now, you guys have a good community, so that's already you guys are steps ahead of me and the opportunity I had. Uh, Second thing is find good mentors. It's really, really helpful. I think that was what started off my journey. I mean, again, like if I look back at things that connected, I was part of the IEEE robotics team at that time. I started off, that was so one of my seniors, he was doing robotics. So I was like, started talking to him, what he was doing, learn from him. Um, Through him, I got connected to a few seniors who had just graduated, who were working with some really good professors. So I got in touch with them. He started to mentor me, guide me. Um, he ended up getting a PhD from Dartmouth on medical imaging, and so I'm still in contact. But he told me, he corrected me on a lot of things here and there. Like you do get deviated at times. So I would be like, one of the incidents I remember is like I was really excited to go to for an ISEC internship in I found in my second year. I was like, okay, this is great. And again, nothing against it. It's great. But I think the part that I was at that time getting excited was I'll be going to Spain. And it was like, I'm getting to travel. I'm going to get have fun. And I wrote to him asking his opinion, and he literally thrashed me. I still have that 2 page long email saying completely like that. You're giving me a life lesson that, okay, you're going to get a lot of opportunities. And since then, so don't think about it. Don't get deviated in your thing. If you want to do robotics, go for it. If you want to do something else, go for that internship. But if you want to do robotics, focus on what will be better for you. Rather go to Triple IT Hyderabad, rather go to IIT and do an internship, learn more about robotics. So having good mentors who correct you, that will be really helpful. Um, Third thing, the certificates you're collecting, they are good for nothing at any level. Like pretty much do not do that. Do not care. If you put your certificate in your resume, I'm going to probably not look at it because I know that you care about certificates. You're already disqualified for me. Don't care. It's not going to work. Nobody gives anything about certificates. Mostly what cares is what have you learned from it? What were your life lessons? What were your takeaways? And what are you interested in getting? So that's where I think my journey, let me give a brief about. So I started off, I very early started taking part, first year, first semester, started taking part in Tech Tattva, autonomous competition, started to take part in all the competitions. I mean, it was weird at that time I mean, I was really interested, but I was the only person then working with all third year and fourth year students. So it was like intimidating, but that's where it helps you build your profile. I was doing great. Then after that, I started to go deep, learn more about robotics. I was really obsessed with trying to learn about small aspects, going from building small mechanical robots to tele robots to just trying land followers, different sensors, a lot of embedded robotics. My first break came with I got an internship with IIT Kanpur at a professor robotics lab in IIT Kanpur, where that was my first experience building real robots. So we were building pipeline inspection robots. Again, great experience. That really led the platform for me to like, okay, I want to go deeper into it. I have some more experience. The first few are the hardest to find out, hardest to get. So it's always going to be super challenging to first to find few, and then things build on, and that's why it looks good to connect back. Uh, that experience connected me to what led to like that was a very rich experience that then I kept working on it. So even after I came back to Manipal, I was still working on the paper I was working at that time. I stayed connected to the professor. I stayed connected. I basically kept working on that research. Uh, then I applied. I think the biggest breakthrough for me was getting into the Robotics Institute Summer Scholar Program at CMU. And that was hard because I was the first, I think I'm the first person ever to get into the program from Manipal. I don't think I've anybody before me got into um, that program. I think now we have had a good channel. I think last year a few people got in. Three folks from our have three folks at least I know got into CMU Robotics MS program. So again, I think we have a good thing building up. Uh, but it was not that. So I think getting that breakthrough was really hard. Uh, and that led to a lot of things. I was working on 15 projects in parallel in second year. So I was doing a lot of things, working a lot of my time on that, just going deep into robotics. One difference was I was doing research. I was focusing on getting better at robotics, just learning more about robotics. A lot of people at that time were focusing on being part of groups, getting certificates, being part of societies, events, those things. I don't think, I mean, for what I wanted to do, that was not the goal. That wouldn't have helped me. So I think getting that clarity was helpful. Then it just led from there. I mean, my CMU internship was great, but it scared the shit out of me because I felt how underprepared I am. So that almost motivated me enough that, okay, I need to go and learn deep about it. So that's where, and I was given computer vision to work on with no experience in computer vision. So that's where I had met the first professor from Austria who I ended up working. So when I went back, I reached out to him. I already talked to him when I was at CMU. He said, I reached out to him. I showed interest that, okay, I want to work more. I want to learn more about drones, computer vision. He said computer vision for drones is so much harder than doing it for rovers. So he convinced me to do it for that. Uh, he invited me for 8th sem internship. So I had a connection. So I did 8th sem. I did 6 months there. And then it was just, that was my first experience at doing very good basic research, publishing papers. So again, just going deep all the way, find what you like, find your challenges, then try to solve them and go deeper, focus on it. I think that's going to be your biggest. From there on, it builds towards it. Your LORs are, again, for me, it was fortunate to work with the right people. So one thing for admission, I mean, this is probably just a stepping ahead. Like if you're looking for grad school admissions in any of the top four, CMU, MIT, Stanford, Berkeley, um, they don't care about anything that your grades are. They don't, I mean, your grades, everything needs to be good. They don't care if your GRE is 330. They don't care if your GRE is uh, anything beyond that. They will care if it's a 290 or something. So what you need to avoid is any red flags. I was on the admission committee, so I'm aware of how the CMU hiring process works to some extent. Don't have any red flags. And if you have a red flag, explain it. So if you have a C minus in your math, you should be able to explain that semester I was either doing something, I was taking a break, I was focusing on this because I really wanted to. That needs to come as part of your story somewhere. But if you have a red flag, I mean, if you're applying for math, if you're applying for robotics and if you have 3 C's in your math, I'm not going to pick you. So it's just simple as that. But I don't need straight A's for everything. Don't have red flags. But just as a very high level breakdown of what we look for, I would say I personally and most of the people I know give 70% or more value to your recommendation letters. Next 20 to 25 to maybe your essay. Everything else falls in the last 5%. Uh, so it's really, and we know when you have written your recommendation letter. So please don't write it. No matter how bad somebody writes it, make them write it. Because I'm going to be reading your essay, I'm going to be reading your recommendation. It's very easy for me to say that you have written the same, no matter how good you are at manipulating that. Don't do that. That's an immediate throwaway uh, for grad school. So again, focus on that. So I focused on that. I think I got that as an advice. Work with good people. So if you want to build a good profile, work on, get focused, get deeper into any field, and then find the best people in the world who work in that field. Try to get to work with them. If those people say that you are good, you're going to get in wherever you want. Um, Looking back, how JPL worked out, again, the same thing. Uh, Everything looks easy. So it's like 2 years. CMU, I was fortunate to work with the best professor at CMU. He's the leader in computer vision. He's now the dean of the computer science school, Marshall Hebert. Uh, the reason I got to work with him was because of one call from my Austria professor that, hey, he's good. 2 years, I worked my ass off to make him happy. That was my only goal, that he really loves the work I do. JPL and CMU are the only places that have been doing robotics for 30 years. One call from my CMU professor will get me admission anywhere. So make him happy, then you get a call. And then it also has to connect the work you're doing. So you have to look for, okay, what are good challenging problems? Once you start to learn more about what's deeper in the field, let's say you go into robotics, you're going to find a specific area of robotics. You'll start to learn, okay, these are the biggest challenges in robotics. Try to work on those, identify those. So I was always looking out. So when I started my master's, I realized that most people were working on computer vision, that were working on data sets, or machine learning, and they were working on data sets. And there were robotics people who were faking computer vision and machine learning, and they were just working on hardware robotics. My professor was the only one who was working on AI that would work on robots, on real world robotic problems. So that really pushed me to work on that. I was excited, I aligned, and that led the gates open for JPL, because for JPL and NASA, we care that, okay, you cannot just develop software, you can develop software that actually work on a system. So again, things connect back. So that was my journey. My journey won't apply as yours. So think about what you want to work on. Who are the people who will make you, who can vouch for you, who will be champion, working with whom will make you lessons, and how will you get to that journey? So thinking from that perspective.
Yeah. Thank you, Shreyansh, because when you're entering bachelor's, you get thrown up with a lot of opportunities, and making the choice to stick to one of them is one of the hard ones because you see everyone else around you getting certificates. So,
Yeah,
yeah.
and that is where you'll have to keep your mind straight. It's very important. There'll be lots of noise around you, lots of people saying a lot of things. So making sure you don't do that is really important. And that's where mentors help. People who have done this before you, attach yourself to mentors. I mean, the folks that, kudos to the folks, your seniors. I have been in touch with several project managers people. I interned, a few of them interned with me. Um, all of them I know are now at CMU master's program. So it helps. It always helps. People who have done that before you know you, they can give you the right advice on things. So find mentors, find good people to work with. I think that's very important.
Yeah. Thank you. And I think we can take one of the questions from the audience. So Akhilesh asks that as an undergraduate in mechanical engineering, how does one pursue research in the field of space robotics? So like how do you get to the starting point and write numerous significant papers?
Don't make writing papers as your, again, that's one of, I think, issues is that people, I mean, obviously there is a thing, you need publications to get into masters. Yes, that's, unfortunately, it is competitive enough that you do need it, but if don't start with that as your goal. If you do great research, you'll get published. That should be the goal. Um, Space robotics is obviously hard to get into, but again, there are opportunities. I mean, when I was there, if I wanted to go more into space, I mean, you may not always get a space robotics option. You don't get that, but you can work for Parikshit. You can work at that time. I don't know what they're doing right now, but they were starting off at that time. You could get some experience of parts of space. You could get some experience of robotics, working through other ones. You can see that, hey, I'm interested in these areas, and okay. I mean, I did not have any space robotics experience. I got it CMU because I had relevant experience of working on robots that could have applied there. I made a story that it could connect and that would transfer. So it's not necessary. You have to show the underlying skills of how you want to do it. At the same time, you can start something. You can start working on a topic, find areas of space robotics you want to get into. There are labs across India that are you can get into. It's going to be super hard. I wrote thousands of emails and heard no replies. So it's going to be hard to get into. But then eventually things just start becoming easy. Once you'll get to a point where almost anybody in the world you'll write to will reply to your email. So it does get pretty easy after that. So I don't know what to answer more specifically about space robotics. Like specifically, I mean, there is a lot of things. People say that you don't have hardware or facilities to work with. There's simulation work out there. I mean, you have a computer, download something. What I'm looking for, if I look for a student, is initiative. Okay, I understand that you don't have a rover to work with. It's okay. I mean, even then, there are people who have like few examples. Like you can reach out to people and work with them, but did you know there are like simulation softwares out there? There are data sets out there. There are things you can still do with something. As a mechanical engineer, I mean, again, it does get hard, but then you can get some underlying skills that have mechanical expertise. Like a lot of the mechanical engineers NASA hires have no experience in space robotics, but they are bloody good mechanical engineers. And I mean, it's not something different. It's just the same thing. So but then you have to be sure that okay, the delta will be maybe you have a lot of knowledge about something, maybe you are enthusiastic about something, maybe you've done, and you have to form a your story of why you are the right person for it.
Okay, that's great. Just
um
before I take
I'll
another,
take a few more
yeah.
questions. I'll take a few questions because I know I was a bit late. I wasted the first 15 minutes. I'm okay with taking a few more questions if people
Okay,
are
we'll
okay,
just
but
do.
please feel free to filter out if you have to go.
Yeah.
No, no, absolutely. It all depends on how much time you have. So maybe we'll do two, three more questions. Yeah.
Okay.
So just a short one, which just going back to one thing which you said, and I think people will have this question because I think everybody has this question is that you spoke about red flags. So in terms of the CGPA, when you can, the US system and the Indian system obviously is different. So in the Indian system, what is a red flag according to you?
So again, GPA, I'm gonna care about it, but I'm not gonna care about it like, okay, some people I've seen like they're gonna try to get this 9.5, 9.7, 9.8 and keep pushing for it. For me, it's not gonna explain how well you're gonna do academically. So for me, I would like you would look for a threshold. Okay, you have a decent. I mean, it's hard to put a number to it. I know I would put a 8.5, 9, whatever. I mean, this it's hard to put a number. It could even be lower than that. It could be higher than that. It really depends. But what I want to get at is, let's say, as an admission committee, if you're looking for grad school admissions or if you're looking to work in an internship or a research, are you academically sound enough? Does your background and experience show that you're academically sound enough to take the hard? Trust me, grad school hits you like a wall. Like I've been telling this to the folks who just got in, and I've been telling them like, be prepared. Like take a few months off if it needs to, but like it's gonna hit you so hard that you don't know because you're not ready for it. The undergrad education in India does not prepare you for that. You'll be doing so many things in parallel, uh, and it's a hard problem. Like one of the machine learning courses I took, it was an advanced machine learning course in my first semester. Uh, it was by Alex Mola, who's one of his lectures are actually online. He's one of the world leading professors in machine learning. And that guy was hell bent on developing his own assignments. And there was one of his assignments, he wanted us to rederive original paper from the 1960s that did not have a derivation. And he went, and there was another question which I had to, for the first time, go to the 35th page of Google to figure out what the question meant. We sat with other machine learning professors to figure out what his questions meant. That was an assignment in a course, one of the 6 assignments, and this was one question. And you get 4 days to solve it or 3 days to solve it, along with 4 other courses you're doing. You are excessively overworked. So it's really, really uh, so you have to be academically sound for it. So if you're applying for a course which is like machine learning or AI, after the first glory nice videos that I showed or everything cool, it's basically straight math from there on. And if you're not good with math and if you're not good with your fundamentals, your linear algebras, your calculus, and those things, you're gonna have a really hard time. I had this when I went for my CMU internship. I mean, I'm suddenly in the room first week or second week into the internship talking about technical work. And suddenly there are people from talking about the rover is not working. They say maybe the Jacobians are off. I'm like, wait, how did this work? How am I imagining a Jacobian? I've studied this number in my math course, but I don't know how that translates to a real robot. So being able to visualize that, and it's very hard. So you have to have very, very strong fundamentals. And that's where the GPA comes in. I mean, I want to see that you, for the courses that you want to be doing, you have done, you have decent background in it, you have done decent work, and you're academically sound on that. That's it. Same for GRE. We don't want to see very low scores. We don't care about seeing very high scores. I would rather have somebody who's done internship, hands-on experience, has a good story, has life lessons uh, to see on a resume than to so a focus. So I would rather see those. So hopefully that answered your CGPA question.
Yeah. So Kaustav Sarkar has asked this question. There's more of a technical question where he's asked that can you elaborate on the terrain segmentation problem faced by rover and what other technologies other than image segmentation can be used to solve it?
Um, Great question again. Like so, that's again that could be an entire presentation on its own. It's a multiple year effort. So there's a lot of effort, things that you could think about. Like we've been thinking about different sensing modalities, like looking at how can you use thermal cameras or multispectral cameras. Can you identify what area is a sand, or if there's a sand trap in front of you, can you identify that by looking at different modalities? So that's something we've been looking into. Uh, there's always, I mean, event segmentation is one of them, but there's another new concept we looked at was put sensors on the wheels. So something we're trying to do is rather than just by image labeling, what we're looking at is as you're driving, you are getting the feedback on your wheels of how well it is. On a hard surface, how your wheels feel will be very different from what it feels on a solid surface, so a soft surface. Can you learn? Can you look at the signals? Can you look at the vibrations on that and learn something from that? So can you So we've been looking at a lot of different ways onto that, but those are two probable ways we've been looking at apart from computer vision.
Okay.
So you said you
So
use sensors on wheels, but I would like to add on. So does that become more of a conventional algorithmic solution, or do you still decide that we might incorporate AI to this data?
Both. So, I mean, again, a lot of this is experimental at this point and research, but we do both of them. So we are looking at how can you in the near like get data, but like you want to make sure where you are, you're safe by getting the feedback at that point. But then if you can use that to learn something in front of you, if you can correlate that with your images that you're looking at, then you can do forward prediction, and then you can use it to plan better trajectories. So we are also looking at that. I mean, there's a lot of ways depending on what your constraints are. So it depends on the mission, it depends on where you're going, what target body it is. I mean, if your mission allows just put a metal detector on it to find tubes, then you don't even need AI. If you have to put a micro rover, you can't even put two cameras. So how do you do everything with one camera? How can you do something with the power? Like one thing I did not talk about with the navigation is energy. How do you develop algorithms that are energy efficient? So let's say you only have 1 hour of sunlight every day. What do you do with it? So anything with space has to be driven down from what the mission is, what constraints you're working with, and stuff like this.
okay, I think we've extended quite a bit. It's just maybe one final question, which is any words of final, any final words of advice or anything you'd like to tell somebody in first year, second year, third year, fourth year in their undergrad right now?
Um, I think it'll be very similar to, let's see, what I already mentioned about the journey and the focus. Uh, it does help to know very strongly what you want to be doing. So I think, and don't try to be in. I mean, there's going to be a lot of people doing a lot of things around you, but make sure you have your own good story of where you want to go. If you can picture what you want to be doing, and it's hard, it's the hardest problem is picturing what you want to do. So setting goals is the hardest part, but try to get to know if you find interest in something, just go deeper in it. Uh, Focus there is no replacement for a focused resume. I think this is just the best thing we always want to look for if somebody uh, on the contrary, if you don't have it, don't fret. It's not the end of the world. Uh, One of my favorite students, persons I have a current summer intern. His background, he's a biology major, and he's doing his master's in statistics, and he's just got into the medical school uh, for an MD program. But he's also working in robotics, statistics and AI, and he is by far the most smartest AI person I know. So if you want to do something, you can still switch, get into it, but really there is no hard rule for it, and we don't penalize for your background. So let's say you're from, a lot of times you pick up a field which you don't really want to, and then you're stuck in working on that. uh, it's okay to change. I have a lot of people who have come from biotechnology, chemical engineering, and they've been still doing robotics research, and they're doing pretty good at it. So focus what you have, go deep into it, find focus a lot about learning and working with right people than getting certificates or competitions. I mean, competitions is a good way to just apply your skill. It's not a good way to build your resume. Don't. So, okay, one of the last things I would say is there was a term that my advisor at CMU had coined. It's called paper champions. We've worked through so many people, and this is specifically a problem when you look at students in India. They are amazing at on paper, and they don't have any depth. Like, I've had people who have written that they know ROS, and they've only gone through the tutorials and run the direct ones. If you have not modified the code yourself and done something, be open about it. Most of the time people are not transparent about it. They think they will say they're an expert at ROS, and they've never done anything beyond use ROS at it. The same for any other technology. Like, especially get this in AI and machine learning, because the starting curve has become so small. Almost anybody within a matter of 1 month of applying an algorithm would say they understand and they're an expert at machine learning. Don't do that. You're just going to basically dilute your own credibility. So I think don't focus on your resume. Your resume will look out. Focus on learning and experience. I never did something that I was told by a lot of my mentors to focus on, which I did not, and I struggle with, is fundamentals. I emphasize, like, I wish I had focused more on my fundamentals as much. Your basic math. So when you go to the CME robotics program, the first course everybody has to take is math. Like, there's a course called Math Fundamentals for Robotics. So everybody has to go back and do math. And so, like, if you don't have your fundamentals clear, you're not going to be going into research. Second thing, because I know there's a lot of folks from the research society here. This is a great experience already. I mean, I had no idea for a while if I even wanted to do research. I was just going into it because it made sense, because it sounded like that what grad school looks for. I mean, that's literally where my motivation came from. Uh, but a lot of people just don't like research. So now that you actually have experience with it, that's great. So experience that, because that's going to really tell you whether you like it or something or not. So, and don't do anything you don't like. You'll be horrible at it. So yeah, I think that's most of the. I mean, I can chat about these topics for hours. But if you have, like, please reach out to me on my email if you're looking for anything. If you're looking for internships, if you're looking for mentorships. I mean, there's one question I always get asked a lot is, I mean, there was one question maybe in the document you said about the opportunities for space exploration for non-US persons in the US. It's a constant question I get asked. Uh, I would say it's growing crazily with what you're saying with the billionaires race, with the space startups, with all of things happening. There's a lot of opportunities that's in space. Don't let that. I'm a non-US person. I'm still a non-US. I'm an Indian citizen still. It's very limited. Again, I'm not gonna be putting you. It is limited. You'll have to be beyond. Like, you'll have to have more expertise than your average person to get into it, because you're competing with a lot of very few positions. But I've understood that from my experience that applies to almost any field. So again, insider tip: all the jobs I applied and interviewed with were never listed online. So none of the jobs, none of the best jobs, none of the best positions are ever listed online. You have to know good people to know people who get through, and that only happens by doing good work. Uh, so if you're doing if you're good at what you're doing, you'll get through. Citizenship, everything else works out. So yeah, focus on your work.
Okay, I think that's great to hear, and just like to say thank you, because it really does mean a lot to people, my friends, and people have been looking forward to this talk, and even people who couldn't make it, people have been asking for the recordings already on the chat. So it does really mean a lot for all the current students because a lot of these things we hear online, we read it on Quora, but then yeah, when it's hard to follow, as you said, right, to have actually have that focus, and then when somebody like you says that okay, I got here doing this, then it does really reinforce that okay, we just have to do these steps. So it really means a lot. Thank you for your time. And I think you're a mentor to Project Manas, so I think although Manas kids will obviously be very familiar with your work, but the Research Society people also encourage you, as he's open to answering his emails. Feel free to send him emails, send him query. So, and that's really nice of you again. And yeah, just thank you very much.
Thank you so much again, Ajit, and all the folks who were in the audience patiently listening. I know I could not address a lot of the questions which are on there. Uh, but I would be happy to reach out. Like, I mean, some of them are very subjective and can take hours of discussion, which is obviously infeasible sometimes. But yeah, again, if you need anything, always feel free to reach out to me. I think it was great. Like, I'm very, very happy and excited, and almost makes me like, I know what's the right word here, but super happy to see what you guys are doing. I mean, I'm amazed at the work you guys are doing. I almost feel jealous that I wish these opportunities were available at that point. I would have been able to do much more. So the fact that you guys are doing this, and I know that you don't get a lot of support from the university. I mean, it's still great. I complained every day when I was there at my university, but everybody does. But looking back, I think Manipal gives you a lot more than you're realizing right now. You will realize that looking back, we have and it's always the peers, like the people you're working with, you learn with, the the vibe around. I think it's just going to teach you a lot of life skills, soft skills that's going to take you significantly further out. And I definitely see that huge advantage. So, and I've had a few very very successful Manipal alumni tell me the same thing. That looking back, I think it's really great what you guys are doing, and it's only getting better. So, yeah, good luck again, guys. You guys are all doing great work. So keep that up. Hope to hear some exciting updates from your side.
Yeah, thanks a lot, Shreyansh. Thanks.
Right. All right. Bye, guys, and please do stay safe.
Thank you.
Bye.
Thank you.
Bye.
Bye. Okay, so that thank you all for attending. That was Shreyansh, and I hope that you guys, we could not answer all the questions due to the time crunch, but I hope most of the people got some answers to the questions which they had in their mind. I'd like to take this opportunity to thank MTTN, who is the official media partner for this event. They have done a fabulous job with the publicity and even the pre-event article, which a lot of you guys must have read. And yeah, they have just done a fabulous job, and everybody knows they are very very good. So I just like to thank them. I'd like to thank people on both sides. They were my juniors. It was completely handled by people in the Research Society and at Project Manas. Yatharth, Kalol, Dhyan, Triti, Supriti, all of you guys. Great job by all of you. Shivansh, pleasure moderating with you. And yeah, I think I hope that everybody was satisfied with this event. And yeah, I hope to see you guys at our next event also. Thanks. See you guys.
Thank you.